In this video, we're testing the convergence of an alternating series. And the way we ordinarily start this out is by testing for absolute convergence, because if we find that, then we get ordinary convergence as well. So what we mean by absolute convergence is we test the convergence of the series of absolute values of these terms. In other words, we simply ignore the negative one to the end part of the alternating series. So we're testing for the convergence of this series. And what I notice when I glance at this is that I have a power of n in the denominator that's 1 greater than the power of n in the numerator. And in the large n limit, this essentially becomes like 3 over n. So this is what informs my decision to do a limit comparison to 1 over n. And that's the harmonic series that we already know diverges. So we set up our limit comparison, and we take the terms of our series divided by the terms of the series we're comparing to, which is the same as multiplying by the reciprocal. And this gives us the limit as n goes to infinity of 3n cubed over n cubed plus 2. Now there's a couple different approaches to this. Informally, I could say that the n cubed in the denominator dominates that denominator. So I can just approximate it as n cubed, cancel the n cubes, and I get 3. A little more formally, I can divide the denominator and numerator by n cubed. Then I say that 2 over n cubed in the denominator unambiguously goes to 0 when n becomes large, and my limit approaches 3. Now when I'm doing a limit comparison and I get a finite number out of it, it means the convergence behavior of the two series that I'm looking at is the same. Since I already know the harmonic series diverges, this shows that our series of absolute values diverges as well. Alright, so this means that our series fails to be absolutely convergent, but it could still be conditionally convergent. So this is where we go into the alternating series test. And to show the convergence of an alternating series, we have to prove two things. First, we have to show the terms are approaching 0 as n becomes large. And to be somewhat formal about it, I can divide the top and bottom by n cubed. So in the numerator, I get a 3 over n. In the denominator, I get a 1 plus 2 over n cubed. And again, we say that the limit of 3 over n unambiguously goes to 0. And the limit of 2 over n cubed unambiguously goes to 0. And this leaves me with 0 over 1. In other words, the limit is 0. So that's the first part of the alternating series test. Just show that the terms go to 0. In the second piece of the alternating series test, and this is always the hard piece, I need to show that the n plus first term is always less than the nth term, at least for n greater than some finite number. And the common trick for this is to actually look at the function of the real numbers that produces the terms in our series. And the reason I have to refer to the function of x instead of n is because I want to investigate the derivative of f of x. Again, when this function is evaluated for integer values of x, it produces the terms in our series. And then if I can show the derivative of this function is negative, then that's sufficient to prove that the next term is going to be less than the previous term. So we take the first derivative, and I have to use the quotient rule for this, so I differentiate the numerator, tack on the denominator left alone, minus numerator left alone, derivative of the denominator. And in my denominator, I have my original denominator squared. And I can clean things up a little bit here. When I distribute the 6x, I end up with 6x to the fourth. And then in the second term, I have a negative 9x to the fourth. So that leaves me with negative 3x to the fourth. And my leftover term from this part of the distributing is a plus 12x. Now we're talking about positive values of x here because we're talking about a series that starts at n equals 1. So the denominator is clearly positive. And then when I look at the numerator, I can tell at some point it becomes negative and stays that way because that x to the fourth term is going to dominate the sum in the numerator. X to the fourth just makes that first term so much bigger than the second term at some point that I'm going to end up with a negative result. So I'm confident at this point that our proof is going to succeed, but it's still a little bit tricky to prove it. So again, the denominator is always positive, so all I really have to look at is the numerator. And to get clarity on this, I'm going to factor a negative x out of it. So I can write it as negative x times the quantity 3x cubed minus 12. Now I can tell that this is always going to be negative, provided that piece, 3x cubed minus 12, is positive. So there's our condition on the values of x that are going to lead to a negative derivative on the function. Solving for x real quick, I add 12 to both sides, divide by 3, and cube root the result. And I find that the derivative of my function is negative, provided that x is bigger than the cube root of 4. Now the cube root of 4 is somewhere between 1 and 2, so I can say that the terms of my series are going to satisfy this condition. an plus 1 is less than an, provided that n is greater than or equal to 2. So by showing the derivative of the function that generates the terms in our series is less than 0 for n bigger than or equal to 2, we've satisfied the second condition of the alternating series test, and we can conclude that our alternating series converges. And there's a special name for an alternating series that fails the absolute convergence test but passes the alternating series test, and that is conditionally convergent. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.